Good afternoon, very pleased to introduce Todd Ringler.
Thank you. Thank you for that kind introduction, Hillary. Where's our, there we go. Okay, the plan here is 30 minutes of material and then 30 minutes of discussion, plus or minus, depending on whether we have anything to discuss and whether or not I can actually keep my material to 30 minutes. Okay, so what I want to talk about is this idea of multi-resolution global climate modeling. So two things. One is Frank asked me during lunch, what is multi-resolution modeling? It's a great question. I think you could refer to it, some people will call this multiscale modeling. Some people will call it variable resolution modeling. And I think there's a whole spectrum in there. So variable resolution approach is we simply take a system that we think we have all the physics, we apply different resolutions at different places and we simulate it. Multiscale to me, and has actually kind of already been applied a bit in climate modeling, is we really have a scale separation. We have a direct simulation of cumulus clouds. We have a model that directly simulates that, and we figure out some way to connect that micro scale model up to a macro scale model. So multi-resolution sits in between, as I hope to show you, and how this terminology fleshes out in 5 years, I don't think we know. The other part of this talk is this roadmap to dynamic adaptivity. When we met 3 years ago to put together this Newton Institute, one of the big things we were talking about was how do we make dynamically adaptive simulations of, in my case, the climate. Other people had other interests in GFD. And so this is kind of a waypoint. I'm going to talk about static mesh refinement, not dynamic mesh refinement. So the strategy here, about the time that we met, we were putting 2 papers together. And so I think I'm going to go over a couple different papers, but I think in total, it includes work of about 13 people. So none of this work would have been possible without really all 13 of those people. So I'm representing a broader group here, and you can get an idea of the folks that have contributed simply by the co-authors of the papers I put up. But we were putting together 2 papers, which essentially just was a generalization of the C-grid. Nothing more, nothing less, but it did allow us this opportunity to use different grid resolutions in different parts of the sphere. And the strategy in the last 3 years for me has been entirely devoted to simply taking the scheme, all of its good parts and bad parts, and pushing it and seeing how far we could go with that scheme. So the first system that we tested, like any other valid global modeling approach, we started with the shallow water equations. And that paper took about 2 years to put together. But what we did in the global shallow water equations, we made a suite of meshes. And these meshes are Voronoi tessellations, or spherical Voronoi tessellations. These meshes actually all have the exact same number of cells and simply distribute them differently on the sphere. And we asked the question in the shallow water test cases, if I distribute my degrees of freedom differently on the sphere, can I get a better answer? And we've restricted ourselves here to simply 2 dominant scales, right? We have called a high resolution region and a low resolution region. There are certainly scales in between that connect these 2 regions, but if we actually made a plot of resolution against a histogram of resolution, we would see that essentially 90% of our cells in this case are in the high resolution region, and then about 10% of our cells are in this low resolution region. And the reason we made the grids like this is because shallow water test case 5 has a mountain, something that someone might resolve, or at least an analog to something that someone might want to resolve in a global climate system model. And so we focused our high resolution region around this mountain and ask the question, can we get more accurate simulations by doing so? Well, here's the game. We're going to run a whole bunch of, we're going to run a sequence of variable resolution. So this is a by 2. Can't tell, but this resolution is twice as fine, by 4, by 8. We got a whole sequence of these. I'm going to crunch them all through the shallow water test case suite and see if we can get a better simulation. It turns out no. It turns out that, so there's 1, 2, 3, 4, 5 different meshes that are run on a whole, that I think are run at 5 different resolutions. So there's 25 simulations plotted on this, and they all fall onto a line. And they fall onto a line of, here's my air, shallow water test case 5, compared to a reference solution. Here's the air. And if they all fall onto a line, the important thing is what's on my x-axis, right? What is the thing that's going to predict the quality of my solution? And the thing that predicts the quality of my solution is the coarsest mesh resolution, the coarse mesh resolution. So I know going in, it doesn't matter which of these I pick. My global L2 air after 15 days simulation is only a function of my resolution out here.
Excuse me, but do I understand correctly that you pick those meshes more or less arbitrarily, right?
Yeah.
No, you didn't, right?
Well, I mean, I put in shallow water test case 5, the entire solution comes from the presence of a mountain.
This is where the grid is refined.
Right, but the alternative approaches and the approach that is used in other disciplines is that the people solve some optimization problem.
Absolutely, right. So you could approach this from a goal-oriented adjoint method as well. And correct.
No, this is not dynamic.
This is not dynamic. I mean,
You can even do static adaptivity using some solving optimization problem.
fair enough, and we have tried to do that, and I'm not saying that we've done it right. But if you try to, what happens here is a Rossby wave is produced, and it propagates clear around the sphere.
Sure.
And if you want to get a better simulation, you have to do a better job of simulating that Rossby wave clear around the sphere. So if you try to do that statically, you end up with resolution everywhere.
So that's the point.
The assumption was wrong.
It's the difference between, let's say, short time forecasting and climate. That's the.
Absolutely, this is about climate. This is about, can we use a multi-resolution approach to get a better climate simulation? Because the folks that do weather prediction, of course, have shown time and time again that you can get a better deterministic forecast.
But then the comparison with the, let's say, the fixed number of degrees of freedom may not be, at least not correct, and because you may not have needed so much resolution, but you needed a minimum resolution in the back.
So, fair enough. And but this is, it doesn't matter what my mesh is. You can think of this as a continuum. For shallow water test case 5 at day 15, I can predict my air by knowing my coarse resolution region. So, the point is, if I'm developing this method to get a better air metric in my shallow water equations, I'm dead in the water. Now, it's early in my talk, right? So,
But the error measure here is over the whole globe or just on the refined region?
exactly. It doesn't matter. Right, so you can go in and say, I only want to look at my air around in my high resolution region. It has been contaminated by that Rossby wave or those gravity waves that have propagated around the sphere.
How do you control the refraction and those kind of things when a feature goes into the high resolution and comes out to a low resolution, comes out and
So in this case, everything's well resolved. There are no features near the grid scale, and so I think in here, we have not seen any spurious reflection. Actually, I don't think there probably is any reflection going on. We're looking at large-scale Rasley waves mostly, and some gravity waves going into the geostrophic adjustment. Okay, so like I said, it's early in the talk, so all isn't completely lost, or I wouldn't have started here. But the red flag number one is, if the air is controlled by the coarse resolution grid, why would we even consider using a multi-resolution approach? Basically, this is a system that's highly hyperbolic, and the information is propagating around the sphere multiple times, and it's going to sooner or later touch the coarsest resolution of the mesh, and it's going to carry with it forever the solution error that it adopted there. Okay. Undeterred, so we move on to the ocean. We're going to do the exact same thing. I presented some of these results last week, and the results last week were quite a bit more promising. And this paper has just been submitted to Ocean Modeling, and happy to share it. But we're going to do the exact same thing. We're going to have a suite of meshes with a high resolution region here, a low resolution region here. And again, I showed this last week, so I'll go quickly here. Doesn't matter where we look, it looks like a smoothly varying mesh. So here's some stuff I didn't present last week. This is, I showed a plot of the kinetic energy, but the movie of the kinetic energy I showed last week was the movie of the global quasi-uniform 15-kilometer. This is from one of those variable resolution simulations. It has about 8 kilometers here in the North Atlantic, and then has about 40-kilometer resolution elsewhere. And you can tell, I mean, there is more structure here, right? These eddies that we see in the North Atlantic actually fill the world ocean, but we don't see them in the world ocean. We only see them in the North Atlantic. We see the Agulhas rings, but they are far more lethargic than we saw in the other simulation. We see the Kuroshio, but it's just a western boundary current. It is not a fully developed, turbulent, meandering western boundary current. But the one thing you don't see is any obvious spurious results due to the mesh transition zone, right? The mesh transition zone, I showed you that movie last week, goes right through here. And I think to the eye, you can't really pick out where the mesh transition zone is. So a more difficult, this is the same simulation, but this is for vorticity, and the color doesn't come out so well here. So you'll see right at the beginning, right there, you see a whole bunch of gravity waves being, or a whole lot of noise due to noise in the initial condition. But then it settles down into a rotationally dominated flow. We get our loop current with our loop rings, western boundary current separating off. You can actually see as the simulation goes down, the North Atlantic current kind of begins to tilt over with matching the observations better. You can actually even see a bit of the northwest corner, Grand Banks, current looping around. And even with this, right, the mesh transition zone is here, and even in the gradient of the velocity, the flow here doesn't appear to be significantly rougher than, say, the flow up there. Yes?
You're not using the same kind of measure as for the atmosphere. There you're only using the qualitative feature.
Right. Quantitative feature.
Okay.
Quantitative feature is, and I showed this last week, this is sea surface height variance. So this is a measure of how well we're simulating the eddies in the North Atlantic. This is from observations. This is from the quasi-uniform. This is from the variable resolution with 15 kilometers in the North Atlantic. And this is from the variable resolution. The movie I just showed was 7.5, 8 kilometers in the North Atlantic. Now, I really should, if I really wanted to make a point to this community, I would have another figure here that showed what is the variance if I had a 40-kilometer mesh. And the reason I don't show it is because there was hardly any variance at all. The Rossby radius of deformation isn't resolved at 40 kilometers, so baroclinic instability isn't resolved, and so I don't get baroclinic eddies. So, green flag, red flag. If the multi-resolution approach allows for a new process, in this case, mesoscale eddies in the ocean, to be permitted that weren't otherwise permitted, then we have hope here, right? This is the simulation if I use 15 kilometers over the entire sphere. This is a simulation if I use 15 kilometers over the entire sphere. This is if I use 15 kilometers just in the North Atlantic, and I get essentially the identical answer. So there's a flip here, right? There's a switch in the sense that if my goal is formal error reduction of a PDE, I might be on shaky ground, but if by adding resolution in a certain region, I get a new physical process, and somehow that physical process is determined by the local flow conditions, then this appears to be a valid approach. Okay, so the last system I want to go through is doing the exact same thing, but now in a full physics atmosphere model. And we started in a particularly difficult system for this approach. We did it at Aquaplanet. We did it in a system that has no zonal asymmetry. The climate and all the statistics about that climate should be zonally symmetric because it's all forced by solar insolation and SST, and all of that is zonally symmetric. But we're going to do the same game, different system. We're going to run a whole suite of quasi-uniform simulations. We're going to run a suite of variable resolution simulations, and we're going to compare these two, particularly in the high resolution region, and ask the question, can these reproduce these in the high resolution zone? Quasi-uniform simulations. So if we run this, kinetic energy, power spectrum for 30, 60, 120, 240, k to the minus 3, k to the minus 5/3. We begin to pick up that transition zone in the 30-kilometer simulation at somewhere around 400 kilometers. As far as a quasi-uniform simulation goes, this is fine. These are just snapshots of precipitation, which I don't think are particularly important here. So now we're going to do the exact same thing, but we're going to put this high-resolution region, and we're going to center it on the equator. So the equator is going to go right across here. It's about 60 degrees in diameter, so north to south, going from plus to minus 30, east-west.
But it doesn't go around the equator. It doesn't go around the
It does not go around the equator, right? Because that's, to me, that's somehow cheating, because half the Earth's surface is between plus and minus 30. So if I go all the way around the equator, I should have just done a global high-resolution simulation and been done with it.
But you could focus it just on the equatorial belt, and then have
right. Yeah. So we could focus it down a bit. Yeah, and we'll see reasons why one might want to do that. But sure, right. So we're going to have trade winds that are going to come in from the east. We're going to have intense precipitation along the equator. We're going to get a Hadley cell, and all of those features are going to know that there are two meshes that exist. There's a coarse mesh and there's a fine mesh. But before we get there, this result could not be better. We compute the power spectrum, but we only compute the power spectrum over the high resolution region. we take both the global 30-kilometer mesh and the variable resolution mesh, apply a filter to it, a Gaussian filter, that pulls out this piece of the simulation and do a transform on that. That corrupts the scales down here, but does not corrupt the scales out here. And these two power spectrum lie right on top of one another. And in particular, we get this transition to minus 5/3 whether we only have a high resolution in this region or we have a high resolution over the entire sphere. So I think this goes along with the previous result that if some new phenomena, in this case, this transition from k to minus 3 to the mesoscale, to be simulated is mediated by local processes, then the approach might work, right? If my question of interest is, what is controlling this transition, I can study that problem, I think, as well in this model as I can in the global model.
Todd,
Yes.
is the spectrum computed at what time step? Is it like
No, so we've computed so for example, right here, we computed the spectrum at a month, a year, 2 years, 3 years, 4 years. There's 6 different lines right there, and they all fall on top of one another. It's the spectrum comes into equilibrium very quickly,
so
as
basically
someone pointed out to us last week.
are you taking a spectral transform and take the coefficients from that you compute the power? You take the
Yeah, that's how you, right. The power is the coefficients of your eigenvectors. Yes. Okay. So now here is it says total precipitation, a Hogg-Mahler. So time is running down, and then this is going from west to east. So we have eastward propagating precipitation complexes. And this is if I have 30 kilometers everywhere. This is if I have 240 kilometers everywhere. And this is if I have 30 kilometers in this belt, plus or minus 30, and 240 elsewhere. So this is a section right along the equator. And so what we're looking for here, first and foremost, is are we getting these complexes that are generated as they come into the high resolution region? Are we getting westward propagating complexes because they're reflected off of the outflow region? Actually, it's coming, or the outward, where the waves propagate out of the region. Or are we getting anything spurious happening at the mesh transition zone? And again, to the eye, I think if I didn't tell you, if I didn't put these lines on here, I think we would be hard pressed to really tell these three apart. But I'll let you look at that and make your own determination. But I said here, the parameterized precipitation's on the right, and there is nothing on the right. The total precipitation is the sum of the resolved precipitation, the large-scale precipitation, and the cumulus precipitation, the parameterized precipitation. And while all 3 of these simulations get about the same total precipitation, at least in this measure, this metric, the models are partitioning the precipitation completely differently. Almost all the precipitation is parameterized, or coming out of the cumulus in the 240, but significantly less is parameterized in the 30. The 30-kilometer simulation is resolving a much more of the precipitation. And so what's the variable resolution simulation to do? It's stuck. It does the best it can. It acts like the 30 in the 30, it acts like the 240 simulation in the coarse region. It tries to act like the 30-kilometer in the high resolution region, but the heating field you get is different whether, the vertical distribution of the heating is different whether the precipitation is resolved or parameterized. So the heating field, the vertical distribution of heating is different in the variable resolution model out here than it is here. And so you get an asymmetric response because of the physical
What do you use for? Do you use like a convection parameterization and a cloud scheme in this run?
No, there is no cloud scheme. I mean, there is no.
So you don't have a microphysics.
There is
scheme
no-
that would sort of.
What is your
Yeah.
parameterization?
But yeah, basically,
But-
the thing is, at some point when you increase the resolution, the microphysics takes over.
Right, exactly, but we're not there, right? So we run, so it's the exact same CAM4 physics package with no tuning of parameters with resolution.
But there will be a large-scale precipitation scheme and a convection scheme, which will take care of convective precipitation, both shallow and deep.
Correct. And that is on in all of these simulations, right? Because we're only at 30 kilometers. We're not even close to the point where we can turn off a cumulus parameterization and think we can resolve that process.
But that's kind of my point. I'm surprised that you get so much less precipitation in the top picture, because if I look at similar IFS simulations, I don't think it has such a dramatic effect, basically.
Fair enough. And so do you have any insight here?
IFS has different deep and shallow. So CAM, the deep and shallow convection are very sensitive to the resolution. It's more, I think, I don't know which aspects, but they're very sensitive to the resolution, and the deep convection becomes much too active as you increase the resolution.
But what we see here is total precipitation, correct?
On the left.
So if the deep becomes very active, then the microphysics becomes weaker.
Yeah, but there is a parameter.
Or maybe it's the other way around. Sorry, it's the other way around. The deep is basically shut off, and the microphysics does all the precipitation.
Right. Yeah.
How is the the large scale precipitation aware of the local resolution? Usually there's you adjust some threshold with the resolution. So it means that you need new batteries probably.
Do you have your phone on you?
I was going for it.
But this is an issue of CAM. This
Yeah.
is a feature of CAM physics.
But I think it's right. So if we turn this into a discussion of cumulus parameterizations, I'm dead in the water. Okay. So let's move on. So this is the same picture, but in a different perspective. So this column is total precipitation. This column is column integrated water vapor. And it's the exact same physics run in all three of the models. I think of large-scale water vapor, or as column water vapor, as a feature of the large-scale atmosphere. Yet, we see that between 30 and 240, we get a completely different distribution of water vapor, in the sense that the 30 kilometer wants an atmosphere that's much moister than the 240. So what happens when we put this into a variable resolution grid? Remember the trades, the winds are coming out of the east towards the west. You know, when the winds come into the high resolution region, it's bringing with it a statistically equilibrated climate from the 240. So that's drier than what the 30 kilometer simulation wants. And so it moistens it. And then once it moistens it, it eventually forgets that it came from a 240 kilometer simulation. And it begins to act like a 30 kilometer simulation by having more precipitation, even hints of a double ITCZ that we get in the 30 kilometer simulation that we don't get in the 240. And it carries that information out with it as it exits, and it even acts a bit like a 30 kilometer simulation downstream of the high resolution region until it eventually dries out and becomes equilibrated to the 240 kilometer mesh again. So So I think this is a red flag, right? I think if the total response, and I'm not sure I'm actually saying this right, there's probably other ways to say this. But, you know, if the total response, meaning resolved plus parameterized to a physical process is 1, important, and 2, is sensitive to grid spacing, then the method is a suspect. Right? If we don't have a seamless transition for of going from parameterized to resolved, then we're in trouble. And I would say that this is actually a problem in all global climate models, even quasi-uniform. Because here I've run, let's forget just for a moment about the variable resolution approach. Let's say I only have these two. There's, which do I believe? This is a large-scale feature. This feature, water vapor, is well resolved at 240 and at 30. But I've gotten two completely different distributions because of this feedback with the, primarily in this case, the cumulus parameterization. So which do I believe? We see this across the board, that we run a whole suite of simulations and nothing converges. Nothing converges because the physics continue to act differently at different scales. And we can somehow ignore that when we only have one scale because we can tune, right? If we don't like this, we can tune some parameter to get a structure that we do like. But it's much more obvious, and I think it's a bit harder to swallow when we have this variable resolution simulation, because clearly we're not going to be able to tune to make this simulation better.
What about the noisiness of the total?
Right. So this is just graphics plotting. This is plotted on the native hexagonal grid. You can actually see the hexagons, and I think Sarah interpolated these others to a lat line grid. I think we fixed that in the final version that was accepted. John.
Well, maybe if the physics is resolution aware, then the things could be more or less independent. But if we have a much higher resolution simulation, then we expect that it's giving us something more. So maybe in the scale, just the way we look at the simulation at the result, there are some scales that are well predicted, and then some other scales that are gained from getting high resolution.
Right.
The way we plot them on the physical world.
Right.
So it doesn't tell us what are the scales exactly, but we just look at it more or less with eyes. But there should be some scales that are resolved, and then later
Right.
on some other.
Right, and so I want to believe the high resolution simulation as well. I want to, in my heart, I really do. But when I have, I didn't go through it but it's in the literature. You know, large scale quantities that are extremely well resolved at this resolution change when you go to here. It's not as if the only thing that changes when we go from here to here is the stuff near the grid scale, right? The influence of the physical parameterizations propagate or contaminate, depending on how you want to say it, up to the global scale. But
So it's the same. I mean, if you look at turbulence, it's exactly the same. I mean, if you look at the features on the large scale, then when you start resolving the feature on the tiny scale, your core scale solution changes dramatically. That's what turbulence modeling is about. The feedback on the small scale and the large scale. So it's exactly the same thing. I mean,
but
will get the same sort of effect.
But here it is, right? My large scale is the same.
True. Yeah.
You know, I call this a great success. I mean, I call this that I could not hope for anything better here.
Is the opposite true actually as well? Like if you do the spectra for the rest of the points in your refined resolution? I mean, like
we didn't
averaged only over the high resolution region, yes?
We're applying a smooth filter to this and then taking that max out all of the coarse resolution. So we're essentially taking transform of this high resolution region
But did you do the?
We
just
did
take-
not do
take
the
out high
opposite,
resolution
but,
and look
and that would be a good idea.
to see what the.
I'm pretty sure that we're going to see exactly what we expect to see. Yeah.
There may be something vicious, is that maybe the physical parameterization originally was overfitted. And you were asking a large resolution method to reproduce features. So you play with the parameters so that they would do that more or less. But then when you change the resolution to higher and higher resolution, then
Right.
yeah, because you've already fitted your result with the low resolution. When you have the resolution, then you destroy this fit more or less. So it becomes harder to.
I have no idea how to fix this. But I think we can agree. I hope we can agree. I mean, I don't see how we couldn't agree. There's a problem. I mean, okay, so, so this is what I'm going to press on. I'm completely undeterred here. I'm taking this to the bitter end. Okay, whether it works or whether it doesn't, and the bitter end is, globally multi-resolution coupled climate modeling, because I think that even with all these problems, for a certain class of scientific questions, this method will work very well.
There are a lot of folks working on that, fixing those parameterizations.
Well, yeah, and I think we'll come to that next. Right. Okay. So what have we learned, or maybe what have I learned, or what do I think I've learned? I think I've learned 4 things. The first is that phenomena that emerges due to changes in local structures, and I haven't learned anything that isn't obvious. Okay, first and foremost. Phenomena that emerges due to changes in local structures are a natural fit for this method. So, to get mesoscale eddies, I need available potential energy at a scale that allows baroclinic eddies to grow. And that's largely a local process. I mean, it's not local in terms of 1 Rossby radius, but it's local probably in terms of 10 or 20 Rossby radiuses. For the results that we've generated, cascading turbulent motions, this transition to 5/3 needs the ability to resolve that scale locally, probably within 4, 5, 10 eddies in either direction, something like that. So this is somewhat obvious in retrospect, but I also think phenomena that are sensitive to local boundary conditions might be better represented with this approach. Orographically forced precipitation, ocean dense water overflows, so sill overflows creating deep bottom water, ocean ice shelf interactions. I think in general, if we fleshed out this list, we would find that there are more of these potential fruitful areas in the ocean and ice systems than there are in the atmosphere system. So on the flip side, right, results that are sensitive to far field forcing will likely not benefit from this approach. Shallow water test case 5 being one example. And then also, for example, precipitation in the southwest has a huge signal that comes from ENSO. If I could put all the resolution I want in the southwest, but if my ENSO is still poor, then I essentially have the wrong large-scale structure, and so adding all of the high-scale structure in the southwest isn't going to do any more than give me better pictures of the wrong answer. So I think that the biggest limitation to this, I mean, the method has to be used in the correct way, but the biggest limitation right now is that we lack a physical parameterizations that act appropriately across scales. And Mark is exactly right. We didn't need this new method to be able to say this. We've known this has been a problem, at least in sort of atmosphere cloud modeling, for 40 years. But somehow I do think that the ability to have these multiple scales in a single model has invigorated the work on this. And so I think I'm done.
Can you put up your precipitation picture here? I just want to, yeah, something like that. So I think this is indicative of the need to, of the, well, the observation that if you have a region of interest, that's not necessarily the only region you want to refine. You may not even want to refine all of that region, but you may want to refine elsewhere. So suppose in that picture my region of interest was like the left hand of the circle.
Mm-hmm.
But I refined that whole circle. Wouldn't your results look better where it got wetter there? It got wetter in the left, right?
Right.
So I said my goal was to get the precipitation, the wetness better, or well, to get that well. And then the right hand of that region, it didn't do so well, but in the left hand it did. But if your goal was just to get the wetness well on the left end of that region,
Right.
and you refine that whole region, you'd get a better answer.
Absolutely. So we need simple stories to tell, right? And I can come up with a couple of simple stories like baroclinic eddies in the ocean. If you want to get a better job of baroclinic eddies here, you need to refine here. And I can communicate that to the ocean modeling community, and they get it because it makes perfect sense. So what we need is just one. We only need one example where we have demonstrated this. And I think we don't have an example yet.
Yeah.
And so we just need one simple example where we show that to get a better answer at X, we put more resolution at Y.
Topography, it's not so,
Well, I
not
mean,
so
there are,
exciting. but
you mean
traffic produced.
you want a simple climate example.
Yeah, exactly. No, it
Examples.
has to be something that connects with folks who actually use the model.
Right.
Right, and so the folks on the ocean modeling, the ocean sciences side that use the model to better understand how mesoscale eddies work, this fits them nicely because they know when they do their analysis, it's the local structure that controls the eddies. So, I mean, I do think there's an example, like sill overflow, right? Dense water overflow. A large part of the world's ocean, deep water, is formed in, ends a relatively small number of sills. And if we put high resolution in that region and get better dense water overflow, that will likely propagate through the entire world ocean and lead to better water masses. But again,
But even, I mean, you showed you get the Gulf Stream pretty good, for example, right? But I mean, what if you only refined half the Gulf Stream, it wouldn't be so, you wouldn't get the Gulf Stream well at all, right?
Yes.
So somewhere between the mesh I showed and a mesh of 1 point, of the simulation is going to degrade.
Yeah, so
But
I
I don't-
told you have to, and it's probably before you get to the Gulf Stream. You have to refine more than the Gulf Stream. You just can't, you could put just a mesh and refine right along where the eddies are.
So this is my concern, and something I raised at PDs last week, is that folks will want to do that,
Yeah, but,
and they will not get the right answer.
well, so that means you have to refine somewhere else, and the question is where and how do you find where to
But I
refine.
think it comes back to Piotr's
Yeah.
remark. It's an optimization problem, and I think I can add that the mesh that produces the best result is not the obvious intuitive mesh. I know from example that were shown to me that the mesh that produce the best results are totally not what the scientists would have constructed in the first place. You have to have an error measure, an objective error measure, and that decides on where the mesh goes. If one tries to decide ahead of time, except maybe for certain features.
It doesn't really have to be objective. One has to know what one wants to know. This is the
Well,
thing.
basically, we want to reduce the error.
But there are like objective errors, and there are like errors which are target some particular aspect.
So
So it depends.
But in the case of climate, you don't want to have the right answer for the wrong reason.
I would say that if you want to benefit from static refinement in the atmosphere, you're not going to get it by going to 30 kilometres in the tropics, because convection schemes work at 240 kilometres, but they don't work at 30 kilometres. So in order to do better than a convection scheme, you need to go to 1 kilometre, which we're not really contemplating. So if you want to do better, you can have high resolution of a region in the extratropics to get more intense precipitation, and it's less reliant on the convection scheme. And then you'll be forced by the tropics, but the forcing from the tropics is then controlled by the convection scheme, which we're not trying to fix with the variable resolution. So I would say that in order to get the better simulation of the southwest United States, it's affected by ENSO. You're not going to resolve ENSO. Resolve the United States better and get the more intense precipitation from having a higher resolution.
But that's not the idea of the convective scheme. Only works at certain resolutions and doesn't work at other resolutions is more of a function of the physics. And you said you used CAM 4, right, for everything? And there's a few reasons why. But for instance, CAM 5, I've seen that if I run a CAM 4 and CAM 5, this effect is still in existence, but it goes down. So the packages are getting better, whether it's tuning or how that works. So I don't know. I wouldn't necessarily generalize and say that increasing the resolution isn't going to get you anything in the tropics, because, for instance, with our cyclone studies, there are completely features that you cannot resolve at 240, and even with whatever convective scheme, no tuning, we suddenly can resolve fairly reasonable statistical quantifications just in equatorial belts at like 25 kilometers.
Yeah, I agree. It's far too general what I just said, but
Yeah.
I think you can see more benefit sooner.
I mean, I completely agree with the discussion where, refining in different locations. Another example would be a lot of, for instance, I mean, you would probably know better, Jean, but for a lot of weather applications, and this is kind of getting into the climate arena, but a lot of studies have shown that if you're able to resolve upstream flow over the United States that's partially orographically resolved, then you produce a much higher quality forecast of your baroclinic wave development coming up the eastern seaboard, regardless of how well you do anything like right at the instance when you're coming up the seaboard. It's all the improvements is the quality of your data that goes in with the upstream wave development. So that's something there. So
I think that's pulling out the hyperbolic nature of the problem.
I might suggest the following, perspective. You say clearly all these effects of resolution are, in many cases, much more obvious for ocean, because in ocean basins are more isolated and communication between basins occurs in very large time scale, right? And from this perspective, if you are looking now about, say, into climate systems, so coupled system of ocean and atmosphere, it really matters, for example, that you have nice resolution in North Atlantic and have gas stream separation properly, because the exchange with atmosphere is strongly affected through this. If you are using ocean model with, say, 1 degree, even half degree, even sometimes quarter degree of resolution, the stream will be just following the coast of US, right? And there will be no cold water basin, and exchange with atmosphere will be fully biased. This is one example. And in order to have this properly in climate system, you need both ocean and atmosphere locally on better resolution, so that exchanges are properly modeled. One more example is the following. Take, for example, Southern Ocean and ice in Southern Ocean, and try to model, again, coupled system. And you see that if meshes are inappropriate and a resolution is inappropriate, you might just lose consistency between, say, albedo that atmospheric model assumes or sees, and ocean model sees. For example, when we are doing coupling in our system with ECM6, we sometimes in summer season see that area of ice is 10% different as it's seen by atmosphere and as it's seen by ocean, just to difference in mesh resolution. So you need to have these things properly done, and there is no other way of doing this as really increasing resolution in these latitudes. Things like that are obviously important, right? And I think that from this perspective, there is no objection, and these are cases which necessarily require a little bit, say, more resolution in certain areas, right? We have to look into dynamics and into dynamical mechanisms that are, say, getting benefits from resolution. If you are just taking aqua planet, perhaps that's simply not the best example. There is nothing area specific.
And that's the exact reason we picked Aquaplanet, because it measures how big the problem is.
Yeah.
Because what I find is that if you take this and you put this in a real world AMIP simulation,
Yeah.
you can't trace back. You don't know what's model error and what is model resolution, because there's so much going on. And so the way you evaluate multi-resolution approaches is you put them in a system that doesn't require multiple resolution,
Yeah.
and ask, do you get the right answer? I think Stefan.
I think, if you look at static adaptivity, what you are looking at is something which has time average scale distribution. That's what you look for, not something which has, time continuous scale distribution also. So you only look at the spatial scale distribution. So if you have a data set, you can do a multi-resolution analysis of the scale distribution on the average distribution. That's going to tell you at this particular spot, on average, in time, I have this particular scale. And then, if you have an obvious separation of scale somewhere, you will be able to put the resolution there. So, it could be one way to look at it, is actually look at the data and do the time average multi-resolution analysis. And in the end, that's going to tell you how fine your mesh needs to be to resolve X percentage of the energy content.
But if I do that for this right here, it tells me I need that resolution I have in the North Atlantic. It tells me I need that resolution everywhere.
I don't think so. I don't think so, because it tells you there is energy at these scales everywhere, but the question is how much energy there is compared to the background flow you want to resolve. And it's obvious to me that if you time average that, you will see a big band of activity, of course, along the equator, in the western boundary currents. You will have an objective way of saying the energy content at these scales. If I want to,
I can definitely look. I can definitely look at data and say which areas are more or less important, right? I can prioritize. But if I ask the question, do I have things that look like mesoscale eddies? I want to put resolution where I have things that look like mesoscale eddies. I end up with the answer. I put resolution everywhere.
sure.
Just like saying if
I'm not saying is there energy at all in the mesoscale eddy. I mean, is there enough energy that I care to represent it? I mean, if you look at your picture here, you can see that of course there's a lot of energy in the mesoscale eddies in the western boundary currents, but very little in the tropics, for example.
On the website there was a question raised by Jürgen Scheppeler, but it disappeared very quickly. But I've seen it, and it reminded me something. Even in the old days, people had done studies with variable resolution for climate, and one of the conclusions was that it was not gaining that much. But maybe there's something to be gained just doing baby step, because ocean modeling is important for it's a monthly or annual forecast. So you can learn. It's not climate yet, but it has feature of both climate and weather prediction. So you can try to learn how to navigate with variable resolution through the system of monthly forecast, seasonal forecast, and so on. And that may be more sensitive to variable resolution than just tackling the climate issue, because, as someone says, maybe the answer for climate is have high resolution everywhere.
Right. Well, so I think right now, if you ask 9 out of 10 climate model users, is it possible to get a better global simulation with a multi-resolution mesh? 9 out of 10 will say no. And that's sort of what I'm getting at the last point here. I don't believe that is always the case. I can think in my head of a couple examples where I think I can get a better global simulation in some important metric by having a different resolution in different locations. That happens to be not in the atmosphere, but in the ocean and in the ice systems. So,
But maybe if there is success with seasonal forecast or monthly forecast,
yeah.
that's enough to justify the approach and further.
Question back here, and then Peter. And
Yeah, especially the coupled models. For the seasonal forecast, like you need to have to predict the mixed layer and its interaction with the atmosphere layer. So the consistent resolution of both the components at one particular place will be desirable. For example, like now the models have, the atmosphere model and ocean model have different resolutions. The future models, like if you could provide a resolution, see for example, for a given point in the globe, both atmosphere and ocean have the same resolution. That could be a variable resolution, part of the variable resolution mesh we have. So that will help to study the air-sea interactions more closely in those points.
Peter, Colin. Peter.
I think that in order to make progress with this, the community as a whole should move as soon as possible to objective mesh generation. Even if down the road conclusion will be now we have to have uniform high resolution. But at the moment, most of those studies are based on so-called experience, or what we think, how the system works. And actually, I don't think that the atmosphere and ocean are primary hyperbolic. They are, and especially so far as climate is concerned, those are mostly elliptic boundary value problems. Everything is connected. Those are global problems. And with moving to this type of objective mesh generation, we will gain certain type of experience that we don't have. Engineers have a much simpler job because they know exactly when they want to have at least approximately they know that they want to have a high resolution near the wing because it's an issue of drag and so on. But our problem is much more complex.
I don't understand. I mean, I absolutely agree with you, but that statement was exactly the same 10 years ago, 20 years ago, right? I mean, multi-resolution models haven't changed that statement. The climate modeling community has never, I mean, you could say objective mesh generation. I could say objective parameterization, parameter specification. Right?
It's very close in reality.
I mean, we have not entrained objective methods in general into any of our.
Well, data assimilation is in some sense objective.
There's very little data assimilation done in climate. I guess. Oh wait, maybe Daryl said much.
So, will, I'm trying to make a question that can be written on a board or something. Will multi-resolution methods determine whether climate warming produces more extreme events? I mean, that's what the man on the street wants to know, right? That's what the funding agents want to know.
Possible. I mean, it's not. I mean, I can't rule it out right now.
Well, I'm thinking that this is you can say this is the reason that in the end we're going to answer this question.
I mean, so
now we're going to make a nice.
You need the right large scale condition. I mean, extreme events. Just like simply precipitation in the atmosphere, right? You need the right large scale conditions, and you need the ability to actually simulate and resolve those extreme events. So you can have all the resolution you want in your region of interest, but if you don't have the large scale inflow right, you're still going to get the wrong answer. If you have the large scale inflow right, but you don't have enough resolution where you are looking to simulate your extreme events, you're still not going to get the right answer. You need both.
that's our responsibility, right, is to answer this question about volatility and global warming.
Well, I'd argue that, and kind of going along with that, so part of number 6 here, one thing, so we're very focused on how we're affecting our solution and the numerics of the problem. But the other thing that we haven't really talked a lot about, and it's more for the physics community, is even if we never see appreciable increase in accuracy or skill with these variable resolution meshes, what I think it does do is it could give physical modelers an ability to develop physical parameterizations in reasonable time frames, as opposed to what we've been doing in the past, which is increase resolution, run a simulation, say our physics are bad, we need to go back and retune, which might help keep, for instance, people have been running the CAM, the community atmosphere model, at a 1/4 degree resolution, and suddenly have said, oh, the precipitation doesn't look as good in some areas, or in actual general as it did at 1/2 degree or 1 degree. And a lot of that's attributed to the physics package, whereas variable resolution setups do give us nice test beds for developing the physics. So even if that itself doesn't produce better climate forecasts, it might give us maybe a 5-year head start, for instance, on.
So that's actually, that was number 5 was
number
5 was a leading question.
Skip by number 5. So.
Yeah. Right.
So what would be a better climate model?
So in that context, a better climate model is one with closer ties to basic physical principles, right? So you take the model closer to the physical basis. It's not better. I didn't mean that question better in the terms of, you know, a better simulation of anthropogenic climate change. I mean better in the terms of more physical realism.
No, I think that yes, there is one. There's the climate of the last century. We can at least agree on that. So ability to reproduce the climate and ability to reproduce higher statistic of that climate with higher resolution.
Right.
And reproducing teleconnections.
Hmm?
If we want to simulate global regional impacts of climate change, we should be able to do teleconnections.
Yeah.
There are metrics.
It's a little bit a poorly posed question, because can this approach lead to the worst prediction? The bottom line is that when you have a variable mesh or adapting mesh, it can, and the proper adaptation criteria, it could also come out as a uniform mesh in a special case. So you cannot do worse, you can only do better. But what we need to understand are how to design the criteria for refinement. Having apparatus of variable mesh is one thing. And another is that once you have it, even when you have this optimization problem for generating those meshes, there is a need to understand what are the criteria, how to set up those monitor functions.
Absolutely.
And this is a lot of work needs to be done, experimental work.
But isn't there some idealized configuration that's close enough to climate that we could use as a toy to demonstrate that?
I think that the progress will come with just doing this on a daily basis, make it easy available to everybody, then the knowledge will improve rapidly.
So I think there's going to be a whole suite of these models that are broadly available in the next 3 years. So people will be downloading them and using them. Maybe I'm less optimistic than you are that it will help. Yes.
I mean, I think it's certainly for research. It's a great tool, and maybe some guidance with respect to how we can learn about the climate on the Earth. Is these Pullman's sort of variable resolution experiment that people have done, where they try to, they applied nudging to sort of have the perfect extratropics